Right now, you're looking at a cosmic crime scene. 400 billion stars in our galaxy alone. 2 trillion galaxies in the observable universe. Planets orbiting nearly every star we've examined. And in all that vastness, across all those worlds, we have detected exactly 0 civilizations besides our own. The silence is deafening. In 1950, physicist Enrico Fermi asked a simple question over lunch: where is everybody? That question has haunted scientists ever since. Because when you do the mathematics, when you calculate the probability of intelligent life arising in a universe this old and this vast, you arrive at an inescapable conclusion. The universe should be teeming with civilizations. We should see them everywhere, their megastructures blotting out stars, their radio signals flooding the cosmos, their probes visiting every solar system including our own. Yet we see nothing. We hear nothing. We are, apparently, alone in an impossibly vast and empty universe. This is the Fermi Paradox, and the solutions scientists have proposed are far more disturbing than the question itself. Today, we journey through evidence that suggests something prevents civilizations from surviving, spreading, or even arising at all. Prepare yourselves. We begin. In 1961, astronomer Frank Drake gathered scientists at the Green Bank Observatory in West Virginia for a meeting that would reshape humanity's understanding of our cosmic significance. Drake presented an equation, now called the Drake equation, that attempted to calculate the number of communicating civilizations in our galaxy. The equation considered 7 factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per solar system, the fraction where life actually develops, the fraction where intelligent life evolves, the fraction that develops technology capable of communication, and finally, how long such civilizations survive. When Drake plugged in conservative estimates, the result was staggering. There should be thousands, possibly millions, of detectable civilizations in the Milky Way alone. In 1961, that seemed like cause for optimism. Scientists believed we'd make contact within a generation. The search for extraterrestrial intelligence, or SETI, was born. But here's where the story takes a darker turn. Since 1960, we've aimed our most powerful radio telescopes at the stars. We've scanned millions of frequency channels. We've examined thousands of star systems. We've analyzed data from the Kepler Space Telescope showing that roughly 20 to 50% of all stars host planets in the habitable zone, the region where liquid water could exist. In 2009, the Kepler mission revolutionized our understanding of planetary systems. During its 9-year mission, it confirmed over 2,600 exoplanets. Statistical analysis of this data suggests there are more planets than stars in our galaxy. Billions of worlds. Billions of opportunities for life. The Voyager Golden Records, messages from humanity attached to probes now in interstellar space, have been traveling for over 4 decades. They carry greetings in 55 languages, sounds of Earth, and images of human civilization. They're moving at 38,000 miles per hour. And they've encountered nothing. In 2015, astronomer Jason Wright at Penn State examined 100,000 galaxies using infrared observations from the WISE Space Telescope, searching for the heat signature of advanced civilizations harnessing energy at galactic scales. He found nothing, no evidence of Kardashev Type 2 or Type 3 civilizations anywhere in the observable universe. The Great Silence, as it's called, is absolute. Let's examine what we know about the universe's capacity for life. Our Sun is just one of an estimated 400 billion stars in the Milky Way. The Milky Way is just one of approximately 2 trillion galaxies in the observable universe. That gives us roughly 1 septillion stars, that's 1 followed by 24 zeros. The universe is 13.8 billion years old. Our solar system formed only 4.6 billion years ago. That means there was a 9 billion year head start for other civilizations. If intelligent life arose anywhere in our galaxy just 0.1% earlier than it did on Earth, a mere 4.6 million years, they would have had time to colonize the entire galaxy. Here's the critical calculation. Even traveling at just 10% the speed of light using conventional propulsion technology we could theoretically build today, A civilization could send self-replicating probes to every star system in the Milky Way in approximately 3.75 million years. That's a geological eye blink. A rounding error in cosmic time. The Milky Way is 105,000 light-years across. Simple mathematics suggests that any civilization, even slightly older than ours, should have already spread everywhere. Michael Hart, a physicist, formalized this problem in 1975. He called it the fact that no extraterrestrials are here on Earth right now. Given the age of the galaxy and the speed at which civilizations could spread, Hart concluded that we must be alone. Completely alone. But there's another possibility. One that's kept scientists awake at night for decades. What if civilizations do arise frequently? What if intelligence is common? What if technological species emerge on thousands of worlds? What if something stops them all? This brings us to one of the most chilling concepts in all of cosmology: the Great Filter. The idea was formalized by economist Robin Hanson in 1996, though scientists had been circling around it for years. The Great Filter hypothesis suggests there's a stage in the evolution from basic chemistry to spacefaring civilization that almost no species survives. A barrier so difficult that it explains the cosmic silence. The filter could be behind us, something extraordinarily rare about the emergence of life or intelligence. Or, far more troubling, it could be ahead of us, something that destroys every civilization before they can spread to the stars. But this represents just one piece of a much larger puzzle hidden in the dark between the stars. In 1960, physicist Freeman Dyson published a paper in Science describing what an advanced civilization might build. As civilizations advance, they need more energy. Eventually, they might construct massive structures around their star to capture all its energy output, what we now call a Dyson sphere or Dyson swarm. Such structures would block visible light but radiate heat. We should be able to detect them in infrared surveys. In 2015, the most comprehensive search to date examined 100,000 nearby galaxies. The result: 0 confirmed Dyson spheres. Not a single galaxy showed the infrared excess that would indicate millions of advanced civilizations harvesting stellar energy. In 2015, astronomer Tabitha Boyajian discovered a star, KIC 846-2852, now called Boyajian's star, that dimmed by up to 22% in irregular patterns. Some speculated about alien megastructures. Subsequent observations revealed dust and cometary fragments as the likely cause. Hope turned to disappointment. Natural explanations won again. The absence is itself evidence. If advanced civilizations were common, we should see their fingerprints everywhere. We see none. Since 1960, SETI projects have scanned billions of radio channels across thousands of star systems. The Allen Telescope Array, dedicated to SETI research, has 42 radio dishes scanning the sky continuously. Breakthrough Listen, launched in 2015 with $100 million in funding, surveys 1 million nearby stars and 100 nearby galaxies. In 2017, Breakthrough Listen scanned the first interstellar object to visit our solar system, Oumuamua, across billions of radio frequencies. Nothing. In 2019, they examined 10 million stars using data from the Parkes Radio Telescope in Australia. Silence. The most powerful signal SETI ever detected, the famous WOW signal in 1977, lasted 72 seconds and never repeated. It came from the direction of Sagittarius. We've looked there hundreds of times since. Nothing. Fast radio bursts, mysterious millisecond-long pulses of radio energy from distant galaxies, initially sparked speculation about alien technology. Discovered in 2007, we've now detected hundreds. All show characteristics consistent with natural astrophysical phenomena, likely magnetars. Once again, nature, not intelligence. The pattern is clear. Every anomaly has a natural explanation. Every mystery resolves into physics, not purpose. In 1948, mathematician John von Neumann described theoretical self-replicating machines. In a space context, These von Neumann probes could visit a star system, build copies of themselves using local resources, and send those copies to other systems. One probe becomes two. Two becomes four. Growth is exponential. Physicist Frank Tipler calculated in 1980 that such probes could explore every star system in the galaxy in under 300 million years, less than 3% of the galaxy's age. Even if the probes traveled at just 10% light speed and took 500 years to replicate at each stop, they'd blanket the galaxy long ago. We found no von Neumann probes in our solar system. We've detected no artificial objects in orbit around other stars. In 2018, astronomers carefully analyzed Oumuamua's trajectory and found no evidence of propulsion or artificial origin. Its acceleration was explained by outgassing, like a comet. Perhaps most tellingly, in 1968, science fiction writer Arthur C. Clarke suggested that alien probes might monitor developing civilizations. In 1973, astronomer Duncan Lunnan even claimed to have decoded messages from a 13,000-year-old alien probe near the moon. Both ideas have been thoroughly debunked. No probes, no watchers, no one home. But this represents just one piece of a much larger puzzle. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published Rare Earth, arguing that while simple life might be common, complex life requires such a precise set of conditions that it's extraordinarily rare. Consider what Earth has that most planets don't. A star of the right type, not too hot, not too cool, located in the galactic habitable zone, away from dangerous radiation. A planet of the right size to hold an atmosphere but not become a gas giant. A large moon to stabilize axial tilt, preventing wild climate swings. A magnetosphere to protect against radiation. Plate tectonics to recycle nutrients and regulate climate. The right atmospheric composition. Water. A relatively circular orbit. Jupiter in the outer system to deflect asteroids. The list goes on and on. Ward and Brownlee calculated that each requirement narrows the odds. Multiply all the factors together and you might get odds of one complex life-bearing planet per galaxy. Maybe one per universe. In 2013, astrobiologist Charles Lineweaver at the Australian National University analyzed the distribution of elements necessary for life across cosmic time. His research suggested Earth formed at almost the earliest possible moment when enough heavy elements existed to build rocky planets. We might be among the first, not latecomers to an ancient party. But perhaps life is common and intelligence is the filter. Life appeared on Earth almost immediately, within 500 million years of the planet forming. But intelligence took 4 billion years. For most of Earth's history, life consisted of single cells. Complex multicellular life appeared only 600 million years ago. Tool use? 3 million years ago. Technology? 300 years ago. Space travel? 66 years ago. Even when intelligence did evolve, it was random. The dinosaurs ruled Earth for 165 million years and never developed technology. A cosmic accident, an asteroid impact 66 million years ago, cleared the way for mammals. Without that impact, intelligent reptiles might never have emerged. Evolutionary biologist Ernst Mayr argued that intelligence might be an evolutionary dead end. Most species succeed by being simple and adaptable. Intelligence is expensive. Our brains consume 20% of our energy while representing just 2% of body weight. Most environments don't reward intelligence. They reward reproduction and survival. On Earth, out of an estimated 8.7 million species, exactly one has developed technology. Those odds are not encouraging. The most remarkable discovery involves how fragile technological civilizations might be. Nuclear weapons appeared 80 years after we achieved powered flight. We came frighteningly close to extinction during the Cold War. On September 26, 1983, Soviet officer Stanislav Petrov saw what appeared to be 5 incoming U.S. nuclear missiles on his screens. Protocol demanded he report the attack, triggering retaliation and nuclear war. He trusted his instinct that it was a false alarm. He was right. One man's judgment saved the world. But it's not just nuclear weapons. Climate change, biological weapons, artificial intelligence, nanotechnology. Each new technology brings existential risks. Some scientists worry we're approaching what they call the vulnerable century, a period where our technology becomes powerful enough to destroy us before we're wise enough to manage it. Astrophysicist Carl Sagan calculated that a civilization must survive at least several centuries as a technological species to have any hope of spreading to other worlds. Most civilizations might destroy themselves within a century or two of industrialization. If this is true, the galaxy might be littered with the ruins of dead civilizations. Worlds that briefly touched the stars before falling silent. Planets covered in radioactive ash or runaway nanomachines or the frozen remnants of climate collapse. The evidence extends beyond simple absence into the realm of terrifying possibility. Robin Hansen's Great Filter Hypothesis provides a framework for understanding the silence. Somewhere between primordial chemistry and galaxy-spanning civilization lies a step so improbable that virtually no one makes it through. The filter could be at several stages. Early filter candidates, the emergence of life from chemistry, the development of complex cells with nuclei, the jump from single-celled to multi-celled organisms, the evolution of intelligence, the development of technology. Late filter candidates, self-destruction through war, environmental collapse, or dangerous technology. Resource depletion, loss of interest in expansion. Physical barriers we haven't discovered. This forces us to reconsider fundamental assumptions about our place in the universe. If the filter is behind us, we're extraordinarily lucky. We're the lottery winners of the cosmos. But that seems unlikely given how quickly life appeared on Earth. If the filter is ahead of us, our odds of survival are grim. Every quiet star system is a tombstone. Every empty planet is a warning. In 2008, economist Katja Grace analyzed the Great Filter and concluded that unless we discover microbial life elsewhere in our solar system, on Mars, Europa, or Enceladus, we should hope we find nothing. Finding simple life elsewhere would suggest life is common, meaning the filter must be ahead of us in the technological stage. Silence means hope. Discovery means doom. Science fiction author Liu Cixin popularized a chilling alternative explanation in his novel, The Dark Forest. The hypothesis predates his work, but he articulated it powerfully. Imagine the universe as a dark forest. Every civilization is a hunter moving quietly through the trees. Announcing your presence is suicide because resources are finite. Any civilization you encounter might eventually become a competitor. Communicating your location before understanding another civilization's intentions is fatal. The safest strategy is hiding, or destroying any civilization you discover before they can threaten you. Physicist David Brin, who proposed the concept of loud civilizations in 1983, warned that broadcasting our presence might be dangerous. Since the 1970s, we've sent deliberate messages into space. The Arecibo message in 1974, the cosmic calls in 1999 and 2003. Some scientists believe this was reckless. In 2015, a group of scientists including Elon Musk called for a moratorium on active SETI, deliberately broadcasting messages to potential alien civilizations. The argument, we don't know what's out there. The dark forest might be real. Perhaps advanced civilizations exist but remain silent, monitoring the cosmos for threats. Perhaps they've learned from bitter experience that announcing your presence invites destruction. Perhaps they're watching us right now, staying quiet in the cosmic dark. Despite the silence, the search for life continues with increasingly sophisticated tools. The James Webb Space Telescope, launched in 2021, can analyze the atmospheres of distant exoplanets, searching for biosignatures, chemical combinations that indicate life. It's examining planets around TRAPPIST-1, a system with 7 Earth-sized planets just 40 light-years away. If life exists there, we might detect it within this decade. The European Extremely Large Telescope, scheduled to begin operations in 2027, will have a 39-meter mirror, the largest optical telescope ever built. It will directly image exoplanets and analyze their atmospheres with unprecedented detail. NASA's Europa Clipper mission, launching in 2024, will investigate Jupiter's moon Europa, which harbors a subsurface ocean with more water than all of Earth's oceans combined. If we find life in our own solar system, even simple microbial life, it would revolutionize our understanding of life's prevalence. The Square Kilometre Array, currently under construction in Australia and South Africa, will be 50 times more sensitive than current radio telescopes. It will scan billions of stars simultaneously, searching for artificial radio signals. Recent breakthroughs suggest we're entering a golden age of discovery. In 2016, physicist Stephen Hawking and investor Yuri Milner announced Breakthrough Starshot, a plan to send tiny, light-propelled probes to Alpha Centauri at 20% the speed of light. The probes would reach our nearest neighbor star system in just 20 years and beam back images. If successful, we could have direct observations of exoplanets around Alpha Centauri by the 2050s. We'd know if anyone's home. Advances in machine learning are revolutionizing data analysis. Algorithms can now sift through petabytes of telescope data, identifying patterns humans would miss. In 2019, an AI system discovered 50 new exoplanets in existing data that astronomers had overlooked. Perhaps most intriguingly, some scientists propose looking for technosignatures, evidence of industrial-scale engineering. Atmospheric pollution. Waste heat from computation. Light pollution on the night side of planets. City lights visible from space. If civilizations exist, their technology might be easier to detect than their biology. The Fermi Paradox forces us to confront uncomfortable truths about our own future. If civilizations regularly destroy themselves, what are our odds? We face climate change, potential AI risks, biological weapons that could be engineered in garage labs, and dozens of other existential threats. Will we be the exception, or another statistic in the Great Filter? Some scientists argue that becoming multiplanetary is humanity's most urgent priority. Elon Musk's stated goal with SpaceX is making humanity a multi-planet species. His reasoning draws directly from the Fermi Paradox. If the filter is ahead of us, our only hope is spreading beyond a single world before disaster strikes. In 2015, philosopher Nick Bostrom argued that existential risk reduction should be humanity's top priority. The permanent destruction of humanity's potential would be an incomprehensible tragedy, not just for us, but for the entire universe. If we're truly alone, we might be the only beings capable of understanding the cosmos. Our extinction would leave the universe forever dark and unknowing. The evidence suggests we're at a critical juncture. We've gained the power to destroy ourselves but not yet the wisdom to ensure our survival. Every other civilization might have faced this moment. The silence suggests most failed the test. After 6 decades of searching, the Fermi Paradox remains unsolved. But the possibilities have crystallized into several competing hypotheses. The rare intelligence solution. We might simply be first. The universe is 13.8 billion years old, but the earliest stars contained no heavy elements, no carbon, no oxygen, no basis for life. Rocky planets with the right chemistry couldn't form until later generations of stars had lived and died, seeding the galaxy with heavy elements. Perhaps technological civilizations can only arise now, and we're among the first. The galaxy will eventually fill with intelligence, but we're at the dawn, not the twilight, of cosmic civilizations. The Great Filter solution. Something kills almost all civilizations. Behind us or ahead of us, there's a barrier almost no one survives. The cosmic graveyard hypothesis. Every star system might harbor ruins. Every exoplanet might be a tomb. We might be next. The dark forest solution. They're hiding. Advanced civilizations know something we don't, that broadcasting your existence is fatal. They've learned to mask their presence, hide their technology, and stay silent in the cosmic dark. We're shouting into a forest full of armed hunters, and they're watching us with pity or horror. The zoo hypothesis. They're watching. Advanced civilizations deliberately avoid contact with primitive species like us, either to observe our natural development or to protect us from cultural contamination. We're in a cosmic nature preserve, monitored but not contacted. The transcension hypothesis: advanced civilizations don't expand outward, they expand inward. Perhaps sufficiently advanced technology turns toward virtual realities, computational substrates, or dimensions we can't perceive. Why colonize stars when you can build universe-scale simulations? We're looking for explorers when we should be looking for contemplatives. The most profound implications emerge when we consider that the answer might be simpler and more frightening than any of these. In 2018, astronomers Anders Sandberg, Eric Drexler, and Toby Ord at Oxford's Future of Humanity Institute published a detailed statistical analysis of the Drake equation. They incorporated uncertainty into every variable and ran millions of simulations. Their conclusion: given realistic probability distributions, there's a substantial chance, roughly 30% to 50%, that we're alone in the observable universe. Not just the Milky Way. The entire observable universe. All 2 trillion galaxies. This finding shocked the scientific community. It suggests that while life might not be impossible, the emergence of technological intelligence might be so improbable that it happens fewer than once per observable universe. Think about what that means. The universe contains more stars than grains of sand on all of Earth's beaches. And across all that vastness, across all that cosmic time, intelligence might have arisen once. Here. Now. Us. If this is true, our responsibility is profound beyond measure. We might be the only beings in existence capable of understanding the cosmos. The only consciousness capable of giving the universe meaning. If we fail, if we destroy ourselves, the universe might remain forever dark, forever silent, forever meaningless. The Fermi Paradox connects to deeper questions about the nature of existence itself. Some physicists suggest the universe might be fine-tuned for consciousness, not because of design, but because of anthropic selection. In the multiverse interpretation of quantum mechanics, universes with different physical constants exist. Only in universes capable of producing observers can anyone wonder why the universe has the right properties for life. We exist in this universe because only this type of universe can be observed. But if consciousness is rare, if the great filter is real and most potential civilizations fail, then conscious observers might be extraordinarily sparse even in universes capable of producing them. We might be looking at anthropic selection taken to its logical extreme. The only civilizations that exist are those that somehow navigate every existential risk. Perhaps the Fermi Paradox answers itself. Perhaps any civilization advanced enough to spread across the galaxy must first develop the wisdom and restraint necessary to survive the dangerous transition from planetary to spacefaring status. The silence might reflect not that civilizations are rare, but that most destroy themselves before they can shout. We're approaching that transition now. The next few centuries will determine if humans join the Great Silence or become one of the precious few who survive to spread among the stars. The universe watches, waits, wonders if we'll make it. We began with a question: where is everybody? We've journeyed through 6 decades of searching, examined billions of stars, analyzed thousands of exoplanets, and scanned countless radio frequencies. We've looked for biosignatures and technosignatures, megastructures and radio signals, probes and patterns. And we've found nothing. That absence tells a story. Perhaps life is rare. Perhaps intelligence is a cosmic fluke. Perhaps the leap from chemistry to consciousness happens so infrequently that we're among the first, or the only. Perhaps the great filter lies ahead, and we're approaching it now with every new technology we develop. Or perhaps the answer is simpler. Perhaps we're not alone, but others have learned what we're only beginning to understand, that survival requires wisdom, restraint, and silence. The current scientific consensus remains divided. Some researchers believe we'll find evidence of life within the next decade as our instruments improve. Others argue the Fermi Paradox will persist, forcing us to accept that we might be alone. But here's what we know for certain: we exist. Against astronomical odds, in a universe vast and ancient, consciousness arose on this small blue world. We can contemplate the cosmos, ask these questions, and search for our cosmic siblings. Whether we're alone or not, our responsibility remains the same. Survive. Spread. Understand. Become the intelligence that fills the great silence with meaning. The universe is vast. The mysteries are endless. And somewhere, perhaps, others are looking up at their night sky, asking the same question we ask. Is anyone out there? The journey continues.